Alright, let's get this show on the road. Ladies and gents, today I'm just going to quickly be going through with you how to multiply and divide uncertainty, or how to multiply and divide errors. And it's going to be two types of things. Errors that have got a scalar, so a scalar which has got like something like that, times 2, and errors that have got, I don't know, something when you multiply two errors by itself. So maybe you don't know what the measurement of the length is, you don't know exactly what the measurement of the time is, so what happens when you multiply both those two things together, or divide those two things together to get a velocity that you still have an error in. Let's jump backwards to see what we did last time. Last time what we did was we started off by talking about what uncertainty is, and then after we talked about what uncertainty is, we talked about why does it show up, because ultimately when you measure something, like even though you measure it, you can still remeasure it and get a completely different value. So we're not really ever too 100% sure what a number or what a value is. We use this idea of plus or minus a half to give an idea of, well, that's roughly how small our error is. Of course, sometimes you use statistics instead. So you might use the standard deviation. In this case here, because it's a ruler, we'd say, and the ruler is measured in millimeters, I would turn around and say, well, this is plus or minus 0.5 millimeters, because it's half the smallest division. It's a pretty good uncertainty. We actually did an experiment where we looked at a couple of different uncertainties using different rulers. We used a red ruler, which had the most uncertainty or the most error, because we were using a ruler with 10 centimeter gaps, and then the green one had the least uncertainty because we were using a ruler which had like half a millimeter or half a centimeter in its accuracy, so we could actually zoom in and get a more accurate, more precise value. Let me just talk about briefly what precision and accuracy is. You can see by this picture over here that precision means you can hit the same spot. So that's usually going to mean that you're getting a really, really small value. It might not necessarily be the correct value. You might not be having very high accuracy, but you will at least be able to get close to the same value. Accuracy you can only really do if you know what value you're looking for. We talked about two types of errors: systematic errors, which is when you stuff up how you're actually recording something, and then random errors that just happen randomly. This is that idea of you might measure something a couple of times, and even though it's supposed to be the same value, it comes out to be like really different values, and you're like, why is this the case? So that's just maybe just something random going on. And so the precision of the experiment is dependent on the random errors. So if you can get a better scale, then maybe you won't get as much craziness going on with your values. So we jumped into evaluating. We're going to skip over this stuff to talk about now the different types of errors. And this is going to be important for later on. So I'm going to go back over this. An absolute uncertainty is usually this delta. And that's these values plus or minus 5. So that's where this absolute uncertainty is. A relative uncertainty is a percentage. It's like plus or minus 5%. So if I have something like 102, that's plus or minus 5 grams. If I go, well, what is that? If that means the delta is plus or minus 5. So how can I work out what the relative error is? Well, to work that out, I'm going to take my 5 grams and I'm going to say, well, what is that out of 102 times 100? To turn that into a percentage. Doing that really quickly on my handy dandy calculator. 5 divided by 102 times 100 gives us 4.9%. 4.9%. Okay, so now if I then go, well, great, cool. That means I could say it's 102 plus or minus 4.9% grams. How do I turn that back? Well, if I've got 102 times 4.9%, or 102 times 4.9 over 100, that's going to give me that should, of course, because I'm using 4.9 instead of whatever came out in the calculator, it won't be exactly correct, but 4.9 divided by 100 times 102, it's 4.998, so 5 grams. Yeah, so I'm pretty happy with that. 5 grams. Cool. So that means I've got 102 plus or minus 5 grams. So the absolute errors have got an actual number, whereas percentage or relative errors have got a percentage. So when we talk about this, it's going to be important later on because you're going to need to know the difference. Now, we then did this quick example of adding and subtracting values of errors. So let's have a quick look at this guy. We've got 2.3. Let's just say I've got a couch. So here's my beautiful couch over here. And I'm going to say, and I've got a table as well. So here's the table. And I'm going to say, well, if I put these end on end, how much space is it going to take up? Well, I know the couch is 2.3 meters plus or minus 10 centimeters. Maybe my ruler isn't that great. But I am a little bit better at measuring the table because it's a bit smaller. So I managed to get it to be plus or minus 0.05. So that's pretty good. Here comes Onyx. Just sit down. Okay, so if I want to add these two errors together, what I would do is I'd say, well, let's just add the values together first. 2.3 plus 0.5, beautiful, done, 2.8, excellent. Now with the errors, I just have to add the errors. So I got the error in the couch is 0.1 plus the error in the table is 0.05. So if I add these together, then that's going to be 0.15, which means that if I add these together, it's 2.8 plus or minus 0.15 meters. So that's the total error. And you can see now the error is bigger than the individual errors. This error here is bigger than this error here is bigger than this error here because you're adding the errors together. You could have, the couch could be 2.2 meters and the table could be 0.45 meters. And because you're adding these errors together, you need to add or subtract the error. You could actually have measured it exactly to be 2.3. So we're not exactly 100% sure. Now, we can follow this logic along now to multiplying uncertainty and multiplying and dividing error. So this is the new content. So let's grab a look at this quickly. So we're multiplying by a constant. Absolute error increase. Errors increase. Relative errors remain the same. So that should be errors increase, but that's okay. But relative errors remain the same. Let's think about this. If you're measuring a if you're measuring like a 10% error, and then you double it, it's still going to be 10% of the original value. So that means this one down here is really, let's just say t total equal 2 times t. So let's go have a look at this one. So if I go 2 times t equals 2 times 5.2 equals 10.4. And because the error stays the same, I can just write plus or minus 8%. Don't need to do anything. Error stays the same. And that's because you're still finding 8% of this value. The percentage error is going to be the same. But when dealing with this situation here, with dealing with absolute errors, it gets a bit different. We would go t equals 2 times, let's go 5.2 plus or minus 0.4. So that's going to become 10.4, right, plus or minus 0.8. So because if you think about it, it's almost like adding. You could think about this as saying, well, going back to what we were doing before, you could almost think about this as adding. Let's take this over here. You could think about this as instead of multiplying by 2, you could say, well, we're taking 5.2 and we're plus or minus 0.4, We're adding that to 5.2 plus or minus 0.4, and doing the same thing that we just did in the previous page back here. You add these errors together, so therefore you end up with 10.4 plus or minus 0.8. Another way you could actually calculate this is you could find 8% of 10.4, and I guarantee you that it will give you 0.8. So multiplying errors really quickly. If the absolute errors, they stay the same. Absolute errors, they get multiplied. So these get multiplied, whereas these ones stay the same. So, okay, so let's talk about this in a bit more detail. Now let's deal with powers and uncertainty. So this is, we're not actually going to talk about, multiplying two errors yet. We're going to get there. So errors raised to powers is quite simple. You just multiply the error by the power. So this isn't the case for absolute errors, of course. I can spell. Yep, ignore that. So let's go have a look at this. Let's look at this formula here. The area of a circle is going to be pi times 4 times pi r squared. That should be a 2. Don't ask what's happened here. 2 times pi r squared. Okay. Why is there 4 in there to begin with? Hold on. The area of a circle is pi times 22.5 plus or minus 0.1 squared. Okay. Don't ask. I have no idea why there's a 4 there at all. Okay. So maybe I got confused with the circumference and whatever. Okay. So what you do is you just multiply the error by the power. So let's deal with this. Okay. So all right. So but we've still got this scalar here, so just keep that in mind. So the area, we're going to do 2 parts here. We're going to do the area calculation here and over here. We're going to do the area calculation over here. So the area is going to be easy. We're just going to go pi times 22.5 squared. So let's just do that in the handy dandy calculator. 3.14 times 22.5 squared, 506.25. Did anyone else get that? No, I've got no one to actually ask because I'm talking to myself. Great. Cool. Okay, so what about the errors? How do we deal with the errors? Okay, so for the errors, we've got to go pi, because again we're multiplying by, and when we're dealing with multiplying by an uncertainty, we've got to remember we've got to also just multiply by the error. So in this case, pi times, now because it's raised to a power of 2 times 0.1. That's where this 2 comes from. And this pi comes from here, which is going to give us 0.2 times pi, which is going to be roughly 0.2 times, 3.14 times 0.2 gives us 0.628. We'll go with 0.63 because why not? So that means the final answer becomes 506.25 plus or minus 0.63 units squared. I didn't actually give a unit here, so it's kind of big. So let's go back over really quickly what we've done here. So the idea that's important here is this. When you square something, that square, and I'll just change my color. When you square something, that square changes into a multiply. The only other thing that was important to understand here is that pi needs to be included in the actual calculation of the error. If you were just squaring the number, like, you were just trying to find the length times the width, you would find the area of the square, then you wouldn't worry about that pi. Because we're doing an actual equation, I thought it would be important to put that in there. Otherwise, you would just, multiply by 2. Let's jump ahead. So let's go have a look at, now we're going to talk about, well, where did I go? Here we go. Sorry. How do you multiply and divide uncertainty? So here's the big one. This is the last sort of one. When you multiply different values with different units, you must use relative errors because they are unitless. And that's going to be important. So let's look at this equation here. E equals mgh. Now that's going to be a formula that we're going to use later on, but today we're just going to use it to look at errors. Energy equals the mass times the gravity times the height. Here we've got 3 different units. And we've got the mass is 0.8 plus or minus 0.1 kilograms. That's not useful because that's in an absolute error. Crap. Well, we can turn that into a relative error quite quickly. 0.1 divided by 0.8 times 100. It's going to give us 0.1 divided by 0.8 times 100, 12.5. 12.5%. So that means our mass is actually 0.8 plus or minus 12.5%. Okay, cool. So now what we need to do is we need to say, well, okay, what about the other ideas here? Well, we've got here gravity is going to be 9.8 plus or minus 5%, and our height's 4.2 meters plus or minus 10%. Now, what's going to happen is the uncertainty in these things is going to compound together. And how it's going to compound together is going to be interesting. Hold on, just let me grab something. I'll be right back. I'm back. So I had to let the dogs out. Sorry. So let's get back to where we were. So we've got these uncertainties. We've got 12.5%, 5% down here, and 10% down here. Now, the trick with multiplying and dividing by uncertainty is you don't actually, for the error side of things, and this is the weird thing, you don't multiply these. Even though they're multiplied together, you actually add them. So what we're going to do is we're going to end up with 12.5% plus 5% plus 10%. That's going to give us, whoa, what happened there? I know I should be able to do this in my head, but I'm not going to because I'm going to make a mistake if I try and do that. Plus 10 plus 12.5, and then that mistake will be 27.5%. Which is pretty neat. So now let's deal with the error part. So let's deal with the actual energy part. So the energy is going to equal mgh, which is going to be 0.8 times 9.8 times 4.2, which is going to give us 0.8 times 9.8 times, whoopsies, 0.8 times 9.8 times 4.2 gives us 32.9. We'll call it 32. I'm going to call that 32.93. 32.93. So that means our final answer, the energy, is equal to 32.93 plus or minus 27.5%. Okay, and then we've got to put a unit at the end, so I'm going to go joules because it's energy. So the idea here is, this is the main important part here. You have to add the errors. If you think about it, it sort of makes sense here. You wouldn't want to multiply two percentages together, because then they would make one percentage make the other percentage smaller, and that would make the error smaller. And ultimately, if you think about it, you're making the errors larger overall. So that's sort of how I think about it. Now, what I'm going to go do now is I'm going to look at a couple of questions here. I'm not going to do all of these questions, but these are the questions that are on the worksheet. So let's grab a look at some of these and how you might approach them. So question 4, complete the following to determine the appropriate units for uncertainty. Again, problem number 1 for, I'll do the problem number 1 for the first one here is you can straight up see, hey, we're in trouble. Whoops, give me a second, sorry. I made a mistake there. I pushed the wrong button. I don't want black. I want blue. That's my dog Juno barking outside. So please ignore that for a second. Actually, I might grab her inside. Give me a sec. Okay, so I'm back. So let's go have a look at the first one. And of course, straight up we can see the problem here is we're trying to deal with values that are in relative absolute error, not in relative error, which means that we can't actually just go bish bash bosh, job done. Let's deal with the actual value over here first, because that'll be easy to deal with. So that's just going to be 2.7 times 12.02. And you know, this is the reason why we don't do these very often, because they're actually a fairly difficult thing to deal with. You've got to deal with all these extra bits and pieces. 32.45. Cool, beautiful. So now we're going to convert both of these to absolute errors. So this is the error side of things over here. So we're going to deal with that by going, well, let's go look at the first one. 0.05 divided by 2.7 times 100. 0.05 divided by 2.7 gives us times 100, gives us 1.9%. The other one, this go over here, 0.08 divided by 12.02 times 100. .67%. Now, if I then, because these two things are being multiplied, that means I'm going to add the errors. So the error is going to be 1.9 plus 0.67. .9 plus 0.67 gives us 2.57. George! Sorry. 2.57%. So that means our final value, let's change this to red just to make sure that we've got it. Our final value is going to be equal to 32.45 plus or minus 2.57%. Now grab and the units centimeters. Always check these. And grab a look at that. That's quite difficult because the actual solving of the problem only took us like a second to do. A hard part of this problem is the errors, because I have to calculate the relative error for one, the relative error for the other one, and then add them together. Like, that's the part that takes you a while to do. Now, I'm not going to... The second one's actually even easier because it's actually giving you guys the... It's giving you guys the difference between... You've just got to convert one of these into a relative error, because this one's already in relative error. But you can also sort of see this is in seconds and this is in centimeters. So you can tell then that that's why we need to use relative errors, because we've got different units. The actual end of this is going to be centimeters per second. Now, if I then look at the next one here really quickly, which was, I'm going to change the slide to here. This is the previous one. So this is actually going to be, this is even easier than the last one. So for this one, 2 times, complete the following, determine the appropriate uncertainty. 2 times, let's do the value over here. I'm still in red. And let's do the error over here. So let's go have a look at this. So the value is going to be easy. 2 times 2.7. Because that's what it says here. 1 second. Okay, so the error part is not too bad either for this one. Because remember, it's an absolute error, so therefore and it's multiplied by a scalar or a fixed number. So we just go 2 times 0.5 or 0.05. Sorry about that. So that's going to be 0.1. So that means our final value is going to be, I didn't actually work this out. Sorry about that. 2 times 2.7 equals 5.4. So that means our final value is going to be 5.4 plus or minus 0.1. This guy, that's it. This guy here is even easier, remember? So for the value, 2 times 16, well, that's going to be 32. For the error, well, because we're multiplying by a scale and this is already an absolute error, it's just going to be 8%. The value doesn't change. So that means this is going to equal 32 plus or minus 8%. And this guy down the bottom here, I've already told you, you just got to take that 2 and you're going to multiply that by 0.08 to get the error. And so yeah, that's it. That should be enough to be able to get you through this worksheet. If you've got any problems, please remember to email me. Sorry, this is a bit rough, but this is the first time I've tried to make one of these videos, and it didn't help that there were some problems with the actual page and my dogs were really annoying. So I've learned some lessons now, but hopefully this will be enough to get you through the holiday homework. Yeah, depending on what happens, we may have to move to this kind of teaching for the term 2, but we're going to be keeping you in the loop. Let me know if you get any problems, and I'll speak to you guys later. Bye.